So welcome everybody. Thank you for coming here. Today we have the pleasure to introduce Dr. Ray Sanchez Arias. He's the assistant chair of Florida Polytechnic University, and he's going to talk to us about the impact of applied mathematics in data science. So take the lead, Ray.
Okay, well, thank you. Again, checking you can hear me okay right now?
Yeah.
Perfect. So let me make this full screen. And well, first, thank you for having me to give this short presentation. I have a copy of this set of slides that are hosted on my website. So at some point in the talk, I'll drop the link on the chat for those of you that would like to go back and review anything of what's discussed today. There's a lot of information in this short presentation, and I wanted it to be in such a way that is as informative as possible, but not overwhelm you with too many things. So hopefully you'll find something that you're interested in after this talk, and you can go back to the link I'll share, and all the links should work, and you should be able to follow the resources that are referenced here. So as Dr. Alvaro Ortiz mentioned, I'm Ray Sanchez Arias. First name REI, that's short for Reynaldo, which is the full name that people use when I'm in trouble. And last name Sanchez Arias because the first last name is from my father's side, second last name is from my mother's side. You'll discover that in a second a little bit more when I tell you a little bit more about me. So we'll start with that. We'll start with who am I and how did I get here and why am I talking about these things? Alvaro and I met actually in our hometown, Cali, Colombia, which is where we both got our undergraduate degrees in mathematics. So this is a picture of a beautiful campus down there, a lot of trees. That's the logo of the university. And if you didn't know where Cali, Colombia is, that is in the southwest region of the country. And it's also known for beautiful people, great weather, and everybody should know a little bit of how to dance salsa. It's almost a survival skill to do that. So after that, after completing my bachelor's in math in 2008, I took the adventure of coming to the United States and then wanted to complete a master's and a PhD in computational science with a specific focus, and that focus was in numerical optimization methods. I went to UT El Paso, and then when we did that, we were part of the first cohort of this program called computational science. And as I said, my main focus was in numerical optimization, and it turns out that many of the data mining and machine learning applications nowadays, of course, they rely somewhat in a variety of numerical optimization techniques. So that's the connection of why am I talking about data science nowadays. After completing that, I joined an engineering college in the city of Boston. Was there for 2 years as an assistant professor in the Department of Applied Math. And we decided to move down to Florida, and I was in charge of a master's in big data analytics at a school called St. Thomas University in Miami. And then in the past 2.5 years, almost 4 years, I've been with Florida Polytechnic University as part of the Department of Data Science and Business Analytics. So throughout that variety of places I've been to and departments I've been part of, I have had the pleasure of teaching many courses, right? Courses in typical courses in a mathematics degree. So anything in calculus 1, 2, and 3, or discrete mathematics, or linear algebra, matrix theory, which is such a cool class to teach, to DFQs, to operations research, and so on. But also graduate courses, and as you can see from the ones that are listed here, many of them are in this area of data mining or machine learning, and of course in all of them, I should say, mathematics plays a very, very big role, right? You need to have strong foundations in math and statistics. to be able to succeed in many of these areas. And since I understand you all have a student chapter of the Society for Industrial and Applied Math, I wanted to also mention that I love that society, and I've been a member since 2011. So I went to my account and try to look when did I start being a Siam member, and I call myself a proud member of Siam. So I started as a grad student around 2011, when we also started a student chapter in the University of Texas at El Paso in the math department. And then since then, I continue my membership there. And I'm a member also of some of these activity groups, SciAgs, in linear algebra and optimization, and a recent one in data science. So if you didn't know that there was an activity group specifically to data science, now you know. Hopefully that's some new information. And it turns out that my first conference of Siam was in 2012. It was in Minneapolis, and it was the Siam annual meeting. And it turns out that for whatever reason, the group of people that I was being part of that night, they took a picture, and then we were on the Siam news newspaper. And the funny story about that is that one of our professors back home in Colombia, he's also a member of Siam, and was joking that I was becoming famous because now I'm in a picture of this news Siam news. So that's the first time I appear in one of those. So I'd like to bring that up. In 2016, I actually presented some work in the Siam meeting, and that Siam annual meeting in the summer of 2016 actually was held in Boston. And the reason why I'm showing this slide or talking about it is because I moved, of course, from being a student and a Siam member, being a student, to being a faculty member at this Wentworth Institute of Technology in Boston in the Applied Math department. And it turns out that year, when we started the chapter, they were holding this annual meeting, and we participated in it. And now I was participating as a faculty member, and we were able to take our students to volunteer in the conference, and they had great network opportunities and really enjoy everything they discover regarding applied mathematics. So that's the reason why that's there. And again, kudos to you for studying a chapter and for being interested in the application of mathematics in different fields. And right after that happened, right after that talk, it seems like I was also in one of the pictures. So now I was in a poster. I moved from the newsletter to the poster. So if I escape this for a second and try to zoom in down there, so that's me with the same outfit. So that happened probably the same day after the talk. So if you have the opportunity to go to any of the Siam meetings, there's several conferences, but the annual meeting is great. I highly recommend it, and hopefully you can present some of your work there and participate or volunteer as a student as well. So I used the Wayback Machine to take a look at what was my role as a student. And I'm sure all of you or some of your students down there have specific roles in the chapter. So my role was as a vice president at the time. And this is a 2014, 2013 capture, I guess, November of 2013 capture. So I was happy to be able to find that. So that still exists. And as I said, as a faculty advisor, I was very proud of all the activities we did at Wentworth in Boston. Our applied math majors were super into applications of mathematics in industry, and we were able to visit several of the companies in the Boston area and have poster competitions and participate in recruiting events and try to get people excited about applied mathematics, of course. So I understand that many of you in the audience, likely, of course, you understand that math is important. Likely, you love using math. You're planning to use math in a variety of disciplines and applications. So the title of this talk, even though it's called the discussion of the big impact, I try to put it together in such a way that it's more of me sharing some resources that I know are out there and that hopefully you can discover later on. Because of course, everywhere we look now, there's some sort of data science application. But if we take it from the point of view of applied mathematics, we have a different perspective of why and how things may work. So in terms of data science research and education, which is what I've been doing in the past 6 years or so, well, what is all this about data science, right? And it's the fact that it combines many concepts from many disciplines, including applied mathematics, statistics, computer science, optimization. There's data mining involved. There's machine learning, and it's a very desired skill nowadays, right? And of course, there's plenty of jobs as a data analyst. There's plenty of jobs as a data scientist or a financial analyst or a modeler, and many more. And if you were not familiar, Kaggle actually publishes every year the state of data science and machine learning, where folks that are in the field share their type of job, their domain of expertise, where are they located, what do they use, what tools are they using, what methods they're using. So when I share this link, you'll be able to click on that and see the different responses. On the right-hand side is just a figure that I just really like to show, because of course, strong foundations in math are fundamental, but you got to practice things like storytelling. You got to be good at problem solving. You got to be good at collaborating with others that may not speak, quote unquote, your language. And you got to stay creative and curious about things. So I always like to put this type of slide, because you require both skills in any type of data science application. But again, at the core, a solid foundation in mathematics is essential, of course. So here's some of the drivers of data science in the past 6 years or more. Of course, one of the reasons why we're talking about it is because there's so much information surrounding our lives. Data comes in structured or unstructured format. It may be generated by your connected devices, it may be generated by your smartwatch, by your social networks, by sensors, simulations, and it comes from multiple disciplines. So David Donahoe once said that many of the goals within data science, one of the big ones is that we want to liberate and create knowledge from data, right? And of course, other drivers include the fact that we have access to open source tools. We have easy access to code and data sets. There's many use cases and applications. Every week there's a new one. We, of course, are fortunate to have faster computing platforms and access to cloud computing resources. And despite all of that, there's been great advances in applied mathematics and computer science that have given the field of data science the strength that's needed to have the impact that it's having nowadays. The picture you see right now on the right-hand side is a picture of Florida Polytechnic University. We are in Lakeland, which is the city right in the midpoint between Tampa and Orlando. And it's the newest state university that's focused on STEM education. So it's one of the 12 institutions in the State University of Florida. And as I said, is the newest one, and it is growing. We do have an applied math major that is starting to get more and more attention. There's several engineering degrees, computer science, and we have the data science and business analytics degrees as well. Within my department, particularly, I teach folks that are pursuing a data science degree, a business analytics degree, or graduate programs in data science or engineering management. And since last year, many of the applied math majors are completing what they call an interdisciplinary sequence, in which they combine different data science courses. Their favorites are time series analyses or data mining and statistical learning. Those are like the most popular classes within among math majors. So of course, math, again, plays a big, strong, and fundamental role in data science. Anything from calculus to discrete mathematics to statistics to numerical linear algebra to operations research, statistical learning, discrete event simulation, game theory, time series, machine learning. In all of those that I mentioned, and some that I forgot to mention out loud, math is super important, right? You gotta have a desire to understand why things work the way they work. And of course, if you're well versed in many of the methods, you have a great future in any of these areas. Within my department, the current research efforts revolve around unsupervised and supervised learning methods, text mining, there's research in econometrics, intelligent mobility or transportation analytics, computational biology, big data, and health informatics. That's more or less the main focus within the members of the department right now. And the story I like to tell one more time is that I think it's because of the training in applied mathematics and computational science that I've been fortunate enough to collaborate with folks in several other disciplines that I never thought I would be involved in. So it varies from computational biology to mechanical engineering to health informatics to economic analyses to even aeronautics. And that really served me well in terms of being able to communicate with others in other disciplines, right? To understand what do they mean by a model, to understand what do they mean by their unknown, to understand the type of methods they use and how do they program those methods. So I was fortunate enough to do that. So some work has been published in biodata mining, which is I never thought I would be doing anything related to it, or IEEE publications with folks in engineering or with folks in aerospace and high performance computing. And again, I think the reason for that is nothing but the desire to learn more about mathematics, about how things work, and that's definitely I think one of the reasons why I've been fortunate to collaborate in this different aspects. So before coming to Florida Poly, actually before moving to Florida, I would say my primary role was as an assistant professor at a primarily undergraduate institution, both in Boston and in Miami. But we do have some summer research students. Some of them were coming from the local community college, Miami-Dade College. Some of them were computer science majors or biology. And we managed to work on problems that involve data and statistics. And so that was very rewarding. And I encourage you as a student, if you're a student in the audience, to try to look for these opportunities during your summer. See if there's any potential way to be involved in research and get one experience, right? Here at Poly, Florida Poly, I try to continue that. I have a couple of students that are data science majors that want to do something that is using some of the data science and math skills to give back, quote unquote, in the sense that we're looking at how to be better at educating our population, right? So creating better ways to explore data sets or create better ways to visualize information. We also had the opportunity to host a Fulbright student that came from Western University. He was an applied math major, but decided to come and do research in data science. And of course, if you have applied math and data science, that gives you a great career. So former students have had jobs at financial institutions, at ExxonMobil, at R&D companies. A couple of them are working for the Department of Defense. Some work in the airline and cruise industry, those in Florida. And others work for software and technology companies. So some of them become software engineers, some of them become financial analysts, and they have very, very strong math foundations. This slide that shows supervised versus unsupervised learning. The reason why I included it is because on the second part of this talk, I'll show two examples that are one of my favorite ones in terms of unsupervised learning methods. This plot comes from MathWorks, the creators of MATLAB, and it's a way to, let's say, characterize two types of problems in machine learning. There's others, but at least two. Supervised learning many times is because folks are trying to solve a classification problem. They try to train a model that would tell you if it's the photo of a cat or a dog, or if it's a benign or malignant tumor. or regression models where you're trying to predict a response that is continuous, right? So you're trying to predict maybe the average temperature or the salary, things of that nature. Unsupervised learning, on the other hand, has a different goal, right? The goal is to try to use data, try to see the structure of the data, and see if there's any way to find patterns of groups that share something, right? And one of the methods that's popular in supervised learning is clustering. I'll talk about briefly about it later. Another one is dimensionality reduction. Those are two classical problems in what we call unsupervised learning. And as I said, there's been great developments, right? Developments that are, many of them due to the work of mathematicians. And nowadays there's many methods and algorithms. This is a picture of an interactive display that the folks at scikit-learn, which is a Python machine learning library, put together, and they have on their website. And once you visit the website, follow this link, you'll be able to actually navigate it and see, do I have a regression problem, and what type of methods are out there, and what type of algorithms are out there? Or do I have a clustering type of problem, and how many samples do I have, and which methods are suggested? The nice thing about what they did is that once you click on any of those boxes, the green boxes, you'll get access to an example on how the method works, which is great because if you want to learn it, you can learn it. You can reproduce the example in your Python or R, whatever language you're using. In this case, Python for scikit-learn. And the second thing is there's many references in there for the details behind the algorithms, the details behind the methods. So let's say after this talk, you're interested about stochastic gradient descent, right? Likely if you go to that box that says stochastic gradient descent, you'll find the correct reference, and you can learn more, and you can read about the math because you're interested in it. Others sometimes are interested in the implementation, but I like this site because you can visit both. And another thing I wanted to share is some resources that are free of charge for anybody, and that are great resources, some of which I use in some of my classes. And they're great textbooks to learning more about the field of machine learning and statistical learning. One of them, the one on the far left, is the Intro to Statistical Learning book by James Whitten, which were students of Trevor Hastie and Robert Tibshirani at Stanford. They have a new version that is also free of charge. If you follow the link, you can download the PDF. There's a great book called Mathematics for Machine Learning, where the authors try to guide the reader on the fundamental concepts of mathematics, including multivariate calculus and including matrix operations that are necessary to explore machine learning methods. And the last one, the one on the far right, is a book called Data Mining and Machine Learning Concepts and Algorithms. If you follow that link, you have access to a version that you can read online. So as I said when I started this talk, I hope that you can go back to this and maybe explore, maybe bookmark some of these resources and have it in your reading list if this is an area that you're interested in exploring. Other things that you can explore came and became very popular because of what we're still living, but we started living in 2020 with the pandemic. And that is that there's a lot of online seminars that are opening their doors to a larger community. So there is one that I think is of interest for those in the audience. It is the online seminar on mathematical foundations of data science. And the reason why I mentioned that is possibly of interest is because the audience is expected to be, passionate about mathematics. And if you follow that link, you'll find recordings of their presentations and many times links to the papers that are being described. The University of Miami also have an Institute for Data Science and Computing where they host some webinars. New Jersey Institute of Technology also runs a data science seminar, and they have all their presentations on a YouTube channel. So here's a screenshot of some of them and the folks that have participated in it. and the type of work they've been presented, right? So it may be about statistical methods that are relevant for a particular application. It may be about sparse models. It may be about stochastic processes. So of course, math is involved in all of them. So here's a screenshot of that YouTube channel for the New Jersey Institute of Technology, Institute for Data Science. It's really cool. I subscribe, as you can see from the screenshot, and I try to watch from time to time some of these presentations. So again, many concepts that are useful for data science. We could run through an entire math curriculum and say, well, actually, all of them are important. But in particular, calculus, again, linear algebra, interest in optimization, graph theory, probability and statistics, discrete mathematics, those really play a fundamental role in several of the data science applications. So since this is part of the science student chapter, I also wanted you to be aware of this in case you didn't know, and it's the fact that Siam is also has put together a journal called Mathematics on Data Science, of Data Science. You can still download several of their papers that have been published. There's great work there. And what's better is that many of the authors have taken this machine learning or data mining techniques that are producing great results and have asked themselves, why is it that it's working the way it's working? So, how is clustering working with a technique called t-SNE, or how is why are big data matrices approximately low rank? So these are great papers. It will be a great resource for study group, and it's something that I would kind of recommend that you explore as part of being a part of a Siam member. Another thing is the Siam activity group on data science. You can also subscribe and see multiple things, including new job opportunities or internship opportunities, research that's being circulated in the group. So try to join an activity group. There is one in data science nowadays. And there will be a conference this year, the Siam Conference on Mathematics of Data Science, which I believe there's still time to submit an abstract for a poster. And it will be in beautiful San Diego, California. So great conference to attend. I'll try to attend. And hopefully you consider at some point. And also, the Siam bookstore has a data science section nowadays. So there's several books of the data science series that are fantastic resources. They're great reads. They're books on non-negative matrix factorization, which is a technique that is very powerful for data completion and for recommender systems. There's a book called The Mathematics of Data Science, where they focus mostly on clustering and classification methods. And as a member, of course, there's a reduced price, a special price for Siam members. And another one that I wanted to highlight is the Harvard Data Science Review. I'm taking a screenshot here of a post by Professor Tamara Kolda called Mathematics, the Tao of Data Science. And it's a great read where she is responding to two other great posts, one on challenges and opportunities in statistics and data science, and another one on 10 research challenge areas in this field. And I'm taking a quote from Professor Kolda in this publication, and it's that mathematics is a scaffold to build the rigor needed to meet practical data science challenges that cannot be solved by trial and error, or adding more computational power, or simply enlarging the training data. And I think it really hits the point with this quote. This is the reason why there's opportunities for those of you in the audience that are, passionate about math and there's applications to explore one of the different challenges in data science problems. So this link should work once you click on them, and you can read more. You can read the articles. I think they're great. So I'm going to try to finish and wrap up this with a couple of examples. One is something that I hope is going to sound simple. And the other one on that thing that I mentioned earlier on unsupervised learning. So the first example is something that we do almost entirely in a course called Introduction to Data Science, that some faculty may do as part of their statistics class. And it's the idea of running or performing exploratory data analysis, what we call EDA, right? And of course, we gotta maybe start with some question, and ideally that's the right question, right? So John Tukey, famous statistician, said that it's far better an approximate answer to the right question, which is, it may be often vague, than an exact answer to the wrong question, which can always be made precise. And of course, math and statistics helps us understand and trust the data that we're using and we're exploring. We can, for example, compute measures of central tendency, so typical topic of a statistics course. You may compute measures of spread, you may test different hypotheses, you may explore the distribution of variables, you may try to understand if variables are correlated to each other and how strongly are they. So I'm going to focus on that last one. And I'm going to say that suppose that we have a set of observations collected by the US Environment Protection Agency, the US EPA. And suppose that you have 38 different models of cars, and they store in this object that we're going to call a data frame, which is nothing but a rectangular collection of variables in the columns, and we're placing the observations in the row. With that structure, sometimes we use also the word tidy, T-I-D-Y, as tidy data frame, where every row is one single observation and every column is an attribute for that observation. So imagine also that among those variables, we have the size of the engine, right? And we have also measures of the car's fuel efficiency on the highway, measured in miles per gallon. So you may have other attributes. Maybe you have the number of cylinders that the car has. Maybe you know the horsepower and other attributes. But at least with these two, you can start formulating some questions, right? You can say or confirm if it's true that cars with big engines may use more fuel than cars with small engines. Or you can study what relationship between the engine size and the fuel efficiency may look like. Is it linear? Is it non-linear? Is it true that if one grows, the other one decreases? Of course we can do this, and we can do it visually through plotting our data on a scatter plot, or we can compute things like Pearson's correlation coefficient, right? Which is that formula there that is on the left. And what we wanted to check is, for example, is if as the value of X goes up, Y tends to go up. And if it goes up or down, by how much? Is it a lot, a little, or not at all, right? So this Pearson's correlation coefficient is going to measure linear correlation between two variables, and it has a value that's between -1 and 1, right? And if it's 0, then there's no correlation between X and Y. Roughly, a rough meaning of that may be that a correlation coefficient, close to 0.8 may be strong, and between 0.1 and 0.3 may be modest, right? So here's a plot of those type of situations, and I think you know where we're heading, right? We have a cloud of points. The correlation coefficient is stronger in one of them, and the bottom right corner is 0.9, and it shows that linear relationship between variables X and Y here, which are simulated data for this case. Well, the reason why I wanted to motivate this idea is because despite having one number, it's also important to visualize, right? So there's this great paper called Same Stats, Different Graphs, and it's called Generating Data Sets with Varied Appearance and Identical Statistics. And the group that worked on this work decided to use mathematics and simulation to create, I believe, 7 different data sets that share a lot of summary statistics, including the correlation coefficient between X and Y, including the standard deviation of each variable. The means of X and Y are the same for all data sets, and several others. And they created what they call the data Soros dozen because of this T-Rex here. And one of the motivations for it actually came from social media. Someone on Twitter one day sent a message saying, I'm creating a scatter plot that looks like this, and somebody then coded it, and then somebody realized that actually we can create this generalization of something called Anscombe quartet. And Anscombe quartet is a classical example in data visualization and exploratory data analysis of 4 data sets that are shown in each of these frames that share the same mean for X and Y, the same standard deviation for X and Y, and the same Pearson correlation between X and Y. But of course, that doesn't mean that they represent the same information. And it's because of simply doing something basic in data science, which is, do some exploratory data analysis, you would realize that, well, perhaps using a linear model in the first case on the top left corner may make sense, but that linear model is not that great of a choice for the second one. And of course, in the other two, we got to find out what's going on there. So that was the motivation behind that generalization of the data source dozen. There's actually a cool video of this guy right here that I forgot his name, and he goes and visits the office of one of the authors of the paper, and they have a quick conversation about how did they do it and what's behind the simulation and what statistical properties are preserved to guarantee that these statistical summary statistics are the same, but their appearance is different. So that's an example of something that we do day to day on a data analytics type of project, right? You get data, you need to familiarize with it, you need to understand it, you need to learn more about the nature of the observations, likely you need to visualize it. And this one was very simple, simply a scatter plot, 2 things that we're trying to understand. If you want to learn more about this, maybe you want to check some of these resources. There are different ways to take a look at statistics problems. They're both introductory statistics textbooks. And the one at the far right is one that I recommend a lot because it's one tool that I use a lot. I use R programming for many of my data science projects, as well as Python. But the R for Data Science book by Hadley Wickham is great. And if you Google R4DS, number 4, R4DS, you'll find it. Or if you follow this link later, you'll also find it. So I mentioned this earlier, and I mentioned this when I said, what are some of the drivers behind this, this growth of interest in data science? So of course, one of which is the access to open source code, to tutorials and samples of R and Python code and other languages that are powerful programming languages that have a lot of libraries and packages that we can just use and learn how to use them and not necessarily implement things from scratch anymore. I'm going to jump now and talk about goals of unsupervised learning. I briefly mentioned it when I showed the picture of the classification versus clustering provided by the folks at MathWorks. But I'm going to mention it here because there's 2 problems that appear that I think are fascinating when you think about the mathematics behind it. And then you start thinking about some generalizations or some special cases. And believe it or not, the 2 that I'm going to mention, if you go to Google Scholar and do a search for these 2 methods that we'll discover here, there's still papers about them, and there's modifications about them, and there's different fields where they're being applied. So it's great. It's great. The math is the fundamental math is simple, but it's powerful. So one of the goals of unsupervised learning, as I mentioned, is to discover interesting things about the measurements that we have in hand. Is there an informative way to visualize the data? Can we discover any type of subgroup structure among the variables or among the observations we have? And these techniques in this area of statistical learning or machine learning and supervised learning are of growing importance for subgrouping breast cancer patients by their gene expression measurements, for example. Segmenting or clustering shoppers based on their browsing and purchase histories, working in recommender systems for grouping movies by their ratings assigned by movie viewers, for example, and of course, plenty more. So as I said, we're going to focus on clustering first, and there's a broad set of techniques here that will try to do one main thing, and that is to find subgroups or AKA clusters in a data set. And that means that they're trying to seek a partition of the data into distinct groups, so disjoint groups, so that the observations within each group are quite similar. So of course, in math, we need to define what similar is, and we may use the distance to say, you know, the distance between two data points is small, then they're similar. So to make this concrete, you may want to think about, you know, what's the metric that we want to use. And of course, depending on what you use, there's properties that are preserved and methods that arise. And another thing to keep in mind is that it's always good to think about the domain-specific application of your work, right? So it's always good to talk about that person that is more familiar with the type of data you're using, that maybe set up the experiment, that maybe knows more about why a patient may behave in certain ways. So that's part of collaborating, right? And you cannot let that go. You have to talk to them and learn as much as possible about the domain-specific application you're working on. So that may be clustering, right? And there's this technique called k-means clustering, which can be posed as an optimization problem. It has a beautiful solution that shows that the optimal clustering and the optimal way to do it is by finding the centroids, and it's a great read and easy to implement. There's also PCA as part of unsupervised learning, but here we're not looking for clusters, we're looking for groups. We're looking for what we call a low-dimensional representation of the observations that explains most of the variance in our data, right? So what we're observing here is a cloud of points in one direction and another direction, captured by these two vectors. And believe it or not, the first direction or the first vector is representing the first principal component, and the other one is representing the second principal component. And if you stare at this plot for a second, you will notice that, well, you know, you have a cloud of points, but they're spread out in this direction that we have found, and there's more variance explained in the first principal component than there is in the second one. But the beauty of it is that the second principal component is built in such a way that is orthogonal to the first one, right? So all of those concepts that you may have learned, you may have heard about, or you may have used in the past for orthogonality and you know, Grant-Smith process and beautiful matrix factorizations like the singular value decomposition, they're super powerful to find the solutions to this type of problems. So that's the difference between those two, between dimensionality reduction. Classical method is principal component analysis, or clustering. Typical method is k-means or hierarchical clustering, or the one that I'm showing here that actually is assigning a color to different data points and then is leaving other points with no color because it's inconclusive, right? So several things to hopefully read more and learn more. For further reading, what I did is I actually I'm providing you with some slides that look like this ones, where I talk about the relationship between PCA and singular values and eigenvalues. I talk about other type of dimensionality reduction methods, some more modern than others. And I talk about the basics of unsupervised learning, discussing hierarchical clustering and k-means. And finally, we talk about DBSCAN, which is a density-based clustering technique. There's a quick overview, and once you get access to the slides, you'll be able to navigate those and then just explore them more. So that's right at 2:45, which is 45 slides. That's perfect. So I want to thank Dr. Alvaro Ortiz and the Siam student chapter at Georgia Gwinnett College for the invitation. Feel free, please, to get in touch. And if you visit my website, there's multiple ways to contact me on my GitHub or other places. Sorry if I didn't see questions as I was sharing the screen. But what I'll do next is I'll stop sharing and I'll put this link on the chat box, and that way you can explore mine. Thank you. I'm going to mute myself for 1 second.
Wow. That was so.
All right. So what I just did is I shared the link to the slides, and that way you can go back and review some of these things.
Okay, Ray, would you be able to send me that link in an email as well? So I might not lose it on the Zoom.
Right. I'll send it to you. Can I send it to everyone in the chat? Send it to everyone in the chat, and then I'll send you an email. Sounds good?
Yes, that's good. So at this point, let me give you a small show on one of the cameras of your audience over here. So there's some people coming in this side and this side. So now that we're going for some questions, I want to start with one in particular that I heard a lot, and is since you know the nitty-gritty of this data science, can we make a difference between who is a data scientist versus who is a data analyst versus who is a data engineer? Like, what are the main difference between those three roles?
Good. That's a great question. I think as the field grows, it will start specializing more and more, right? So those that are data engineers, things that I'm expecting from them are that they're very good at managing big data. They're very good at data warehousing. They're very good at they're very good at scaling computational power. They know how to set up the cloud services. That they know how to work with APIs to get data, high frequency information. So that's how I would say, okay, that's a data engineer, right? You know about data science in general, but your main focus is computational, and you're really good at the knowledge available for it. A data analyst, on the other hand, I would say is somebody that's very curious about the particular data set they may be working with, right? And that means they're great at statistics, they're great at some modeling, they know how to present data, they know how to find outliers, they can formulate great questions and tell you why missing data is there, or why shouldn't it be there, or how can we impute data when it's missing. And they're great communicators too. And then I will put the data scientists in the middle, saying, well, you got to have some skills of both that we just mentioned, but likely you have very strong foundations, very strong math foundations that allow you to take a technique that we know works, but that when you find a new domain may not work as expected, and you know exactly what to modify, you know exactly what factorization is to be modified, you know why a technique or why an algorithm is not convergent, and you can write your own, right? So those will be at least three characterizations that I will provide in for this question.
Thank you. We have another question in the Q&A. Maybe you can see it. It says, as a mathematician, what should be my focus as someone interested in working in data science? Building portfolio, coding, or maybe more math?
That's a good question. I would say it's good that you're interested in computational skills, that you learn Python or R, and that you can demonstrate that any data set, because the thing is, it doesn't necessarily have to be a data set, let's call it quote unquote, a serious data set, right? It could be a data set that represents something that you're fully interested in and that maybe you know a lot about it. Maybe it's a data set about games. Maybe it's a data set about the NBA players. And can you use something like a dimensionality reduction technique to take 25 different attributes you have for those players and represent in 2 or 3 or 4 principal components the variation among all that data set, right? And understand what's happening behind it. I think as a mathematician, being able to explore those techniques and to extend them and to play with open source code that implements some of these techniques will be great for building your portfolio, right? And maybe building a career in data science.
That sounds good. Is there any other questions you guys have?
I see a question, which is, we still have a couple of minutes. It's asking, do we need a graduate degree to get a job as a data scientist? Do we need internships? I think internships are a great way to start understanding what's needed for the type of organization you want to work for. Graduate degrees, are they necessary? It will depend on what's going to make you happier and for the field that you're planning to go to. What's happening in terms of, do we need new models? Do we need new methods for it? And things that we we couldn't be able to cover in an undergraduate class. I must say though that the undergraduate majors and several of the former students, internships have shown to be great ways to get involved, to realize I'm great, or I love solving problems, like solving applied problems quickly, or I love doing research. And if you really love research, then maybe pursue a graduate degree, right? But if you think you're a problem solver that can use techniques that already exist, you fully understand them and can produce and get satisfaction from it, then maybe go on the job market. So that's the type of answer I think I would give.
Yeah, that sounds about right. Okay. Any other questions? Okay, I would like to thank the speaker for his time. Thank you so much for joining us today. It's been a pleasure. Please.
Thank you. Thank you. Thanks again for the invitation. And, I hope at least one of these links that we share on the slides you'll find useful. And, feel free to reach out, and kudos for the job that you guys are doing there, and stay in touch.